Welcome to another episode of Advanced Rust. In a previous video we saw how we can create threads and how we can share state that was already present in the moment when the threads were created. And if you remember correctly, we did this with Arc and mutexes. If you haven't seen this video, I highly recommend you check it out because it's going to be the fundamental for what we're going to be doing today. The thing we didn't cover yet is how can we share state that gets created during runtime on one thread and communicate it to another thread. And Rust's solution for this are channels. Rust encourages a message passing style concurrency, and in order to make that work, we will be using channels today. I'm your host Max, you are watching Green Tea Coding, so let's not lose any more time and jump right in. So let us start off by creating a channel, shall we? So we'll go into MPSC, which is multiple producer, single consumer. This is just the notation that we have for channels in Rust, which is you can have multiple senders at the same time, but you can only have one receiver for the messages that you put into a channel. And in here, we can create a channel. The first surprise maybe might be that what we're getting back is not one channel object, but instead we're getting two objects back, a sender and a receiver. So let's just destructure this. TX is going to be the sender, RX is going to be our receiver. The second thing to note here is that a channel is always templated or is a generic of a certain type. In this case, we haven't specified the type yet, and we could do so. For example, we could specify that the type will be a string, or we could just leave it up to the compiler to infer the data that we want to transfer from our usage. So note that through one dedicated channel, you can always just send one kind of data. In this case, we're sending strings. Now, of course, channels are being used to communicate between threads. So let us just create a thread. We already know that we have to move everything into the closure that the thread needs. And in this case, we're going to move the TX, so the sender, into a thread. Just import thread as well. And all we're going to do in here is send with our sender a string, and we're going to call unwrap on this send routine. Why do we need to unwrap? Well, a channel can be or could be broken. This is whenever one of the two sides has hung up, or to stay in Rust terms, the sender or the receiver has already been dropped. So if I am the sender and the receiver has already been dropped, however I don't know that, I will not be able to send, which means that the result that we're going to get back is an error rather than an OK. However, in this tutorial case, I know that my receiver is still alive, so I can just call unwrap on here. Going further, of course, we want to receive some of those messages on the main side. So we're going to just say the message will be rx, our receiver, dot receive. And of course, receive can fail in the same way that send can fail. So we need to unwrap here as well, in case our connection, our channel would already have been broken. In the end, we receive some message and we're going to print it out. And because we are a good Rust citizen, of course, we're going to join this thread back in. If we run this example, we will see that as intended, we received this message, message1 from thread, and our program closes down as normal. Let us now explore a bit how receive actually works. In this case, we're trying to get exactly one message and then print it out. However, what would happen if no message will be sent at all? I mean, we cannot be sure of that, right? If we run now, we will see that our program will run indefinitely. This is because receive will block the current thread of execution that it's running on until it receives a message. And if you are not absolutely sure that you will receive a message at some point, your thread might block until the end of time. Especially if it's the main thread, this is a very, very bad idea to do. What you could instead do is you could use try receive. Let me just put that in here. So what we're doing here is we're running a loop for 10,000 iterations. And during those iterations, we're getting a possible message with try receive. try receive is going to be non-blocking, meaning it looks up what is in the channel. If there is no message in the channel, it will just continue and have as a result a try receive error. And if there is something in the channel, it will have as a result a string. Of course, we can match on this. If we get an OK, we know that we received some message in the following iteration. And if we did not receive a string, you could do something else that you want to do on your main thread, but you would not be blocking. Okay, so in this case, if we run now and we're not sending a message, then we will just run through this whole program. We have never received a message in 10,000 iterations, but at least we didn't block until the end of time. If we send the message, we can see in this case we got a message in the 752nd iteration 1248, so that will vary quite a bit. But in the end, we're making sure that we're not blocking our main thread. So this is the second way to receive messages with try receive. Now let's get to the third option of receiving messages. In this case, this would be with receive timeout. So what we're doing here is we're using receive timeout, and we need to bring duration into scope. And in this case, we're specifying a timeout during which we want to try to receive a message. And if this timeout ran out, we're going to continue anyway. So we're saying if within the next 5 seconds we will get a message, then we will have a result of string back. Otherwise, we will get a timeout error. And again, we can match here on the outcome. To make this a bit more interesting, we can put a sleep in here for 3 seconds. Also bring it into scope. And we will see the thread waits for 3 seconds, then it will send a message. Our receiver can wait up to 5 seconds, so it should be able to receive the message. Let's just check if that works. We're waiting our 3 seconds, we send the message, and we receive the message before the timeout. Very nice. If we now don't want to wait 5 seconds, but only for 1 second, we will see that the thread times out. We got no message before a timeout, and we are done. So this is your third option. If you are willing to block your receiving thread, but only for a certain amount of time, you can use receive timeout. So until now, we only sent one message exactly, and we knew that we had one message to receive on the other side. Of course, in a realistic scenario, this is often going to be different. You don't know how many messages you will be able to receive, and therefore you need some kind of an iteration over all the messages that you can get. And it is very, very easy to implement this. In fact, the receiver offers an iterator trait, or has the iterator trait, and therefore you can just write a for loop over your iterator, so for message in Rx, and you will then just receive the messages. So let's try to do this. For example, let's send 2 messages here. Message 1 from thread 1 and message 2 from thread 1. We just run. And in the end, we'll see we received 2 messages and then the iteration terminated. Seems a little bit like magic, doesn't it? Somehow, this loop knows exactly when it is finished. Well, the magic in here is that this loop will end exactly when the channel is broken. And when is this channel broken? Well, once this tx goes out of scope, so this thread is finished, the channel that we created will be broken. Rx, or this loop over Rx, will notice that the channel is broken and will then terminate this loop and will end this loop here. So this is a very nice way to say if I have a thread that is mainly the consumer, or whose only job is consuming messages from a channel, I can just have this as my main loop and iterate over all the messages that we get. And as soon as the channel is broken, I will then automatically know that it is broken because the loop will end. Now let us finally get into the MPSC, the multiple producer single consumer part of channels. If I were to have a second thread, let's say, so thread 2 here, which is also just a thread that I will spawn. And of course, I need to threads2.join in. I should be able somehow to use the same channel because this is a second producer and this channel is supposed to be multiple producers, right? All I need to do is clone the sender, okay? So I can say let tx2 is equal to tx.clone. And you will notice while tx, so the sender part of the channel, has a clone functionality, rx, the receiver, does not. So this goes to show that it is multiple producer, single consumer. I can then move this tx2 into the second thread, and from there I can also produce messages. So if we run this, we see we received a message from thread number 2, then we received a message from thread number 1, and the second message from there. And after everything is done, we can then terminate this iteration down here, and we terminate our whole program. Let us now talk a bit more about the properties of channels in Rust. The channel that you get with MPSC channel is an asynchronous unbounded channel, meaning that you can send even though there's no one there to receive, or let's say no one is currently receiving. Of course, the channel must still be valid, the receiver must not be dropped, but it must not be listening at the same moment that you send. This is what is called asynchronous. So the sender can, for example, just input 5 messages in here without even knowing whether the receiver is currently listening or not. The channel will then internally buffer those messages. And because this is an unbounded asynchronous channel, it will actually buffer an infinite number of messages. Well, that's kind of a lie, because of course you are limited by the memory, the working memory that your computer has. But it will eventually fill up all this memory if you keep pushing messages into the channel without receiving them. We can see this in this example. We're generating 5 messages, and then we're finished, while the main thread sleeps for 3 seconds, and only after that it will try to receive the messages. So let's run this. We see we're now waiting. Thread is already terminating, and now we get all those messages back in the correct order. So channels have the property of being asynchronous, unbounded, and they will maintain the original order in which the messages were put in. There is, however, a second kind of channel that is built into Rust, which is the sync channel, also in MPSC, meaning it also has multiple producers, single consumer, but this time we don't get a sender back, we get a sync sender back. The receiver, however, is unchanged. So this leads us to believe, which is correct, that only on the sender side things will change, while the receiver side will basically stay the same. Also, when you create a sync channel, you need to input a bound. This is the number of messages that can be buffered inside the channel. So if I set this to 1, and then I want to send one message first, and then the second message, the send for the second message will block until the channel has enough space to contain the second message, which is when the first message has been read. So let us run this example here. You will see we sent message 1, nothing's happening. After 3 seconds, the receiver will then receive the first message, and only then we can send message 2, upon which the receiver will, of course, receive message 2. If I would set this bound to 3, for example, we can send both the messages, because the buffer is large enough, and then receive both of them. And what you can actually do is you can set the bound of your channel to be equal to 0. This is what's called a rendezvous channel, meaning that the sender and the receiver will always have to meet first before anything can happen. So I'm just going to start sending one message here, but the sender will block here until the receiver starts receiving the message. So let's see. We run it. We see no output here. And only when we have received the message, then the thread continues after the message has been sent. So here you can again see all the methods that you have to send and receive with your normal asynchronous unbounded MPSC channel. The sender is actually very simple. You only have one send method, and this is non-blocking, so sending is usually not an issue at all. On the receiver side, however, you have to put in a little more thought in order not to block your threads for too long. There are 3 methods that you can receive in a blocking way, which are receive timeout, and iterating. And there is only one non-blocking way, which is try receive. However, with non-blocking receiving, you of course have to make sure that you're not missing out on one of the messages. Again, looking at the overview that we had for the normal channel, we are seeing the sync channel has only very, very little changes. The only thing that changes is actually the sender, which is now a sync sender, and the send will block only if the buffer is full. The rest of the methods stay all the same. As the last chapter in this tutorial, let us now look at a real-world, quote-unquote real-world example of how to use channels. I have the following task. This is my input file, which contains a lot of numbers, which are numbers from 1 to 30. And what I want to do is I want to read those numbers into my program, then execute some mathematical operation on this. In this case, I'm just going to square the number, and then write the results to an output.txt. The main challenge with this is that our program will be what is called I/O bound. So the speed with which we can read the input from the input files and write the output to the output file will determine how long our program takes to run. If you were to do this consecutively, you would first read all the input file, then you would do all your computations, and then you would write all your output file. However, because we know that reading from our file is so very slow, we have a lot of computational power left over that we can use while we are reading elements from the input file. So the idea here is to create 2 channels. One is the channel that will convey the data from our input txt to our main function. And the other one is an output channel, which will then transfer the computation results to an output.txt file. The input is running on a reader thread, which does nothing more than just open a file. Then we have a buffered reader that will read line by line the input file. And whenever a line is read, we will just have a little output here to know what is happening. And we will then send via the channel this input line that we have read, parse it to an i32 first, and then send it. On the other hand, we have the writer thread, which is doing the same thing, but the other way around. We have an output file that gets created. Then we have this writer that will write line by line into our output file. And for every number that we get, so we use the iteration syntax here for num in rx output, we will then first convert a number to a string and then write it as bytes to a file and write a new line character as well to go into a new line. Don't forget, if you use a buffer writer, you always should flush your output before you're done. And this is exactly what happens when this thread here ends. Our main function is where we're gonna having our computation done. So again, we're using the iterator syntax over our rx input, so the values that we read from our input.txt. We're going to have a little bit of diagnostic output, and then our horribly complicated computation will just be a square this time. And when we're finished with this computation, we're going to send the result to our output writer. Note that we need to drop tx output here. Otherwise, the loop over rx output in our writer thread will never finish because the loop waits until the channel is broken somehow. And this is an intentional breaking of the output channel so that the writer thread will be able to finish. Of course, in the end, we will then join everything together. So let's run this for now. And let's look at the output. We can definitely see that we're doing asynchronous processing here. Okay, we're reading the first 3 lines from our input file, and then our main function already processes those 3 numbers. During that time, we're already reading a few extra numbers, we're taking time to process, extra numbers processing, until somewhere in here, we're already starting to write to the output. And in this case, it is coincidence that all the numbers will be written at the same time. If we let this run a few more times, we can definitely see some variance in there. So I've let it run a few times now, and this time we see we have a lot of variants. Now we have always one read, one computation, one read, one computation. And at some point before the last number is read, we are already starting to write to an output. Again, here writing, we're reading, and we're doing computations. So everything is running asynchronously, and we're making better use of the time that we have in between or during the slow reading and writing process. Now that you know the ins and outs of channels and you know how to send and receive data, you're very well equipped to safely and efficiently share data between threads. Use it wisely together with Arc and mutexes to bring your concurrent programs to the next level. If you learned anything new in this video, then like it and consider subscribing as well. I'll see you next time with Green Tea Coding.